Okay, so back to Bohr's model of the atom. And if you remember, the question was, how come Bohr's model is stable when Rutherford's isn't, even though Bohr is still saying that his electrons are orbiting the nucleus? So how come his electrons aren't giving off energy and therefore being drawn in? And so his reasoning was that only certain radii worked. And in those certain radii, the circumference of those circles would be equal to a whole number of de Broglie wavelengths of the electron, right? So de Broglie wavelengths, lambda equals h over mv. If a whole number of those wavelengths fit into a circumference, then that orbit was allowed. But if I'm just going to do a little picture over here, like imagine that you started here, right, and you go around, and when you get back here, like you overlap so that it's not perfectly in phase with each other. So this would be destructive interference when we think back to grade 11 physics of waves, and then like this wave would keep going, and you would have like chaos, and so he's saying if a whole number doesn't fit in, that orbit isn't allowed. If it does fit in, then it creates a standing wave, a wave that looks like it's standing still in the medium, just flipping back and forth, so then it doesn't look like it's actually moving around the orbit, and so then it's not giving off energy, okay? And so he figured it, that's why he figured out the radii for all the allowable orbits. And people were like, oh, okay. And so they're buying this, but there are three limitations, and that's where we left off. So limitation number one was that it could not explain why the spectral lines of hydrogen, or which spectral lines of hydrogen would be brighter and which ones would be dimmer. Now, if we were in school, we would do a lab with the spectral lines, but since we're not in school, we don't get to do it. So what we would do, though, we would put a glass tube with a tube with gas in it, like hydrogen, argon, water vapor, helium. Trying to think of what other ones we have, krypton, a whole bunch of them. So we would put it in a thing like this, which sends a high energy. It's a high energy source, right? So it sends a current of energy through it, which causes the gas to glow, to give off light. Really what it's doing is it's jumping all of the electrons up into a higher level, and then when they fall back down, they emit the light. And then we look at this through a prism, okay? And when we look at the light that's given off through a prism, we see a whole bunch of lines. And so these lines, this is called the spectrum of that particular gas. Okay, so hydrogen has a particular spectrum, a whole bunch of different visible lines, and after we finish here Bohr's three issues, we will talk about the spectrum more. Okay, so hydrogen then gives off a whole series of lines, and one of Bohr's issues was in the visible spectrum of hydrogen, you can see 4 lines. One of them is really, 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 really dim, and the other 3 are quite bright. Actually, when we do it in class, students only see 3, and I'm like, okay, you need to look closer because there's one more there, but unless you're like nose right up to it, it's really hard to see. So one of Bohr's issues was he couldn't explain why. Why were some of them brighter and some of them dimmer? His second issue was in some of the atoms, some of the lines are like almost on top of each other in their spectra. Sodium is probably the most famous for this. The sodium spectrum, the visible lines in sodium are 2 yellow lines that are so close together they just look like one thick one. But if we had high resolution, we'd be able to tell that they were actually 2. But then, of course, the question is, but why are they so close together when in other substances, other elements, the lines are spread further apart? And Bohr's model couldn't explain that. And the third limitation was really the one that, like, it was the major limitation. You couldn't get past it. And it is, sadly, that as wonderful as this model is for hydrogen, because remember he based it all on hydrogen, it does not work. It cannot predict the electron orbits nor the spectra for elements with many electrons. It really only worked for hydrogen, and as you go up, it gets worse and worse. So that's the major limitation. It's like, it should have been good, except the rest. Like he thought if he figured out hydrogen, all the rest would fall in, but they didn't. And so then it was like, shoot, then it must not be quite right. Now, before we go on to what the next model is, we need to pause a few minutes and talk about these spectra. The equations that you were going to use in this unit really are the equations that we got in the last off Bohr. So there's EP equals EF minus EI, the equation for the radius, and En equals negative 13.6 electron volts over n squared. As we go from here, because we're going to be moving into quantum, the calculations will get less for a little bit. So our homework over the next few nights will just be with these equations, just to let you know. So for those of you working on the practice assignment, just know that you'll have time, because for the practice assignment for atomic, know that you'll have time because these ones are it for here. If we were in class, I would do a test at the end of Rutherford, and I would put Bohr on the next one. Okay, so I'd leave these equations for the next one because you'd need some calculations for the next unit. All right, so back to spectra. There are two different spectra. There's the emission spectrum, and plural, by the way, of spectrum is spectra. So there are two spectra that we need to talk, two types. One is the emission spectrum, and the other is the absorption spectrum. And in a way, they're the mirror images of each other. Okay, just like their name implies, we can figure out the light. So spectrum, remember, like the visible spectrum is the whole rainbow of light, and the electromagnetic spectrum is all the radiation. So when we talk about an emission spectrum, we're talking about the light that an element is giving off, emission giving off. When we talk about an absorption spectrum, it's the light that the element is absorbing. Okay, but emission spectrum first. So this is the light that an element is given off as a result of that element being heated by a high voltage source to the point of incandescence. So we go back to here. Here's my high voltage source, and I'm going to put my gas tube in here, and thanks to electricity, I'm going to heat that gas to a point where it's going to give off light. And that point is called to the point of incandescence. When something's heated so hot it gives off light, we say it's at the point of incandescence. It's kind of like if you turn a burner on in a stove and that burner starts to glow, or the burner in your oven, then you've heated it to the point where it's given off light, to the point of incandescence. So when it's glowing, if we look at that light through a spectroscope, which is really just an apparatus that has a prism inside, then that prism's going to break that light down into its separate wavelengths. We will only see the visible spectrum, but on either end there will be the ultraviolet and the infrared, and so if we were to hook the spectroscope up to a computer, the computer could perhaps figure out the lines down here. But with our eye, we're only going to be able to see the visible one. Okay? And so our spectroscope will separate that visible light into its different lines. Now, if we would do the lab, you would see that like hydrogen glows like a purple red. And when we look at the light through the spectroscope, you'll see a purple line and a red line that are really quite bright. And so it explains why we see a purple red. There are others that have a lot of colors all across the board. And when that happens, when you look at the light it's given off, it's more white, because like all the colors together will give us white. But if you see I'm going to run out of time. Hold that